Okay, in this lesson, we're going to be organizing our real and complex numbers, and we're going to do so with a Venn diagram. Now, first off, let me present this. I'm not a huge fan of this Venn diagram, and the reason being is because when you're in the real number system, which let's break this down, here is where our real numbers are located, so I'll go ahead while I'm talking and label these. When you're dealing with the real numbers, a real number is either rational or irrational, and that's what you have here. Here's all the rationals. And by the way, look, let's just use our abbreviations. The abbreviation for real would be just a capital R. The abbreviation for rationals, again, is a Q. The abbreviation for irrationals is an I. A number cannot be not real or not irrational and not rational. It's got to be one or the other. So really, what's out here? So be careful with this because when you're dealing with the reals, you're either rational or you're irrational. And then your subsystems of your irrationals, you have your integers, which our abbreviation for integers is Z. And then inside the integers, you have your whole numbers, which start 0, 1, 2, 3, 4, and so on and so forth. And then you have your natural numbers or your counting numbers, which is abbreviated N. Now you have this whole new system of numbers. You have your imaginary and complex numbers. Your imaginary numbers lie outside of those real numbers. So you're either real or you have this group of imaginaries, or there's a combination of both, and we call these the complex numbers. We're going to use a capital C for complex. So pretty much every number that you have dealt with is a complex number. So now let's classify these. Let's zoom in. We're going to simplify and then tell all the sets that it belongs to. So the square root of negative 64, that's the square root of 64 times the square root of negative 1. So this is 8i. First off, this is a complex number because every number is complex, and this is imaginary. So that's all. It cannot be imaginary and real, so therefore it's complex and imaginary. 10i times negative 2i, let's multiply. That's negative 20. I times I is I squared. So that's negative 20 times negative 1, which is a positive 20, which is a complex number. And then it's either real or imaginary. This one is real. If it's real, it's either rational or irrational. This is a rational number because it's not a crazy decimal. It can be written as a ratio or a fraction. If it is rational, which by the way, Q stands for quotient. If it is rational, it could be an integer, and in this case it is. If it's an integer, it could be a whole number, which is 0 through wherever, all your positive whole numbers and 0, and it is also a natural number because those are your counting numbers. So this is pretty much everything. Number 3, the square root of 1/9. You can split the square root of 1, square root of 9 is 1/3. First off, this is a complex number because all numbers are complex. It's either imaginary or real. This one is a real number. If it's real, it's either rational or irrational. If it can be written as a fraction, it's rational, and it's not going to be anything else. The next one, let's subtract. This is going to be, let's rewrite it, 15 minus 8i minus 9 plus 3i. Combine your reals would be 6. Combine your negative 8 and 3, that's negative 5i. So first off, this is complex. So let's put a C for complex. Then it's either real or imaginary. This is a combination of both real and imaginary, so it is just going to be complex. Okay, number 5. Number 5, we're distributive property. 4 times 9 is 36 plus 20i. Negative I times both would be negative 9i and a minus 5i squared, which turns into a plus 5. Combine your reals, that's 41, and combine the imaginaries, is plus 11i. This is a complex number. It's not pure real or pure imaginary. That's all because it's a combination of both. I to the 41st. Let's remind you that your pattern, I to the first, I to the second, I to the third, and I to the fourth. This would be any multiple of 4, so I to the 40th would be here, so I to the 41st power would be here, which is just plain I. That is a complex number because they all are. That's either, it can be either real or imaginary from here. It is imaginary, so therefore it is nothing else, complex and imaginary. Number 7, cube. Both of these gives you a negative 8 and an I to the third. Square both of these gives you an I squared, and when you square a square root, it removes the radical. Negative 8 times 7 is a negative 56, and we have I to the 5th power. Again, our pattern, I, negative 1, negative I, 1. I to the 5th would be, this is I to the 4th, so here's I to the 5th. So we have negative 56I, which is complex and imaginary. Number 8, complex conjugates. 3 times 3 is 9. Negative 5i times 5i is 25i squared. I squared will be a negative 1, so let's do a plus 25 there, and that gives me 34. When you multiply complex conjugates, again, you always get a real number. So therefore, this is complex. It is real. It is not imaginary anymore. Since it is real, it's either rational or irrational. This one will be rational. Again, the only irrationals are like pi, the square root of 2, the square root of 3, all those crazy decimals. Then now that it is rational, we can check the subsets of rational. It is an integer because that's your positive and negative whole numbers. It is a whole number, and it is also a counting number, which actually a natural number, not a counting number. It's the same thing. Number 9, I to the 16th power. If you follow your pattern, I, negative 1, negative I, 1. All the multiples of 4 are here, so this is 1. So therefore, it is complex, and it is real. Your subsets of real are rational or irrational. This is a rational number. Since it's rational, now we can check all of our subsets. It is an integer, it is a whole number, and it is a natural number. Root 150, this can be simplified. Let's split it into root 25 times the square root of 6. So this would be 5 root 6, which is, again, a complex number, and it is real. Subsets of real are either rational or irrational. The square root of 6 we don't know, so therefore this will be an irrational number, and that's all. There's no subsets of irrational. Okay, next up, let's talk about the properties of complex numbers. Okay, the properties of real numbers, commutative, associative, identity, inverse, and distributive, also be applied to complex numbers. For questions 11 through 15, write an example of the property using complex numbers. First off, commutative property. Commutative property says that things can be added in any order. And an example of that property, 3 plus 4i is a complex number, and that's going to be the same thing as 4i plus 3. It doesn't matter the order you write it in. Or you could even say if you added 3 plus 4i plus 5 plus 6i, that's the same thing as adding 5 plus 6i, and you can check this, plus 3 plus 4i. That's your commutative property. The associative property says that you can add them, you can group them in any way that you want to. And this is the associative property of multiplication. So you can mix some pure reals and pure imaginaries. So like 2 times I in parentheses times 3 plus 4i would be the same thing as 2 times, in parentheses, I times 3 plus 4i. It doesn't matter the grouping. You can do the first two and group them, or you can do the last two and group them. The order of again, the order of parentheses does not matter. Distributive property also applies. And that would be like 5 times, I'm using that same 3 plus 4i over and over, is equal to 15 plus 20i. So you can use distributive property when you're dealing with complex numbers. The identity property of multiplication, again, identity property is anytime you take a complex number and you multiply it times the identity element, which is 1, you get the exact same complex number. The inverse property of addition says that if you add a value to its opposite, so if you add 3 plus 4i to its opposite, let me zoom in a little bit, and the opposite of 3 plus 4i would be negative 3 minus 4i. If you add any complex number to its opposite, then you're going to get the identity element for addition, which is 0. Now, again, let's look at these and let's name the property that justifies each of them. So let's zoom in on just the problem. Which one says that I can take 2i and I can multiply it by both? This would be your distributive property. Okay, number 17. which says if you multiply a value by its reciprocal, you're always going to get 1. That's going to be your inverse property of multiplication. Again, the inverse is the same thing as a reciprocal, and you're multiplying by here, and that gives you your identity element. Anytime you multiply and get the identity element or add and get the identity element, again, those are your inverse properties. So this is going to be the inverse property for multiplication. Okay, number 18. Here you had the negative 5 plus 4i grouped. And then plus 9i, and then notice the order does not change. That's the most important part. This says that you can regroup these, and instead of having negative 5 plus 4i grouped, you can group 4i plus 9i. Anytime you change groupings, that's the associative property. Again, associative, the root word is association. The associative property, since you're adding here, this would be the associative property of addition. Okay, number 19. You added 0, and it didn't change. It kept its identity. Anytime you add or multiply something by 0 or 1, and it keeps its identity, again, that's going to be the identity property, and this would be the identity property of addition. Okay, number 20. Here you have two numbers being multiplied times 8i, and then you switch the 8i first and have the two numbers second. There is a move took place. These switched. Anytime it's a move, that's the commutative property. Since you have multiplication involved, this is the commutative property of multiplication. Okay, number 21. You added a complex number to its opposite. And notice they just put the negative out front, and that's still the opposite of the two complex numbers, and you got 0. When you add a value to its opposite and gives 0, then you added it to its inverse, its additive inverse. So this would be the inverse property of addition. Okay, the next one, number 22, says name the additive and multiplicative identity of 6i. Now, most of the time, I'll call this the identity element. The additive identity element is always 0, meaning that you can add 0 to anything you want and it keeps its identity. The multiplicative identity element is what could you multiply this by to give you it back. 6i times 1 would give you that 6i back. So the additive identity element is 0. The multiplicative identity element is 1. Number 23 says name the additive and multiplicative inverse. Okay, the inverses are what could I add to that complex numbers to give me the additive identity, which was 0. And you can always add the opposite, which would be negative 8 minus 3i. Or you could say that would be 8 plus 3i. Either one of those would work. The multiplicative inverse is what could I multiply this by to give me the multiplicative identity, which is 1. If you multiply anything by its reciprocal, which would be 1 over negative 8 minus 3i, then you always get 1. Now, just a reminder that we could rationalize this. We could multiply top and bottom by negative 8 plus 3i, the conjugate, and we could actually clean that up a little bit as well. Number 24 says for 24 through 28, write true or false. If false, it's provide a counterexample. The set of complex numbers. Now, closure. Closed under addition means you take two complex numbers and you add them together, you get another complex number. That's what closure means. So if I add two complex numbers together, will I always get another complex number? And well, pretty much complex numbers is every number. So if you add two numbers together, you're always going to get another number of some form. So therefore, that would be a true statement. It's going to be hard to get a non-number if you add two numbers together. The set of complex number is closed under division. And again, complex numbers involves every number. So if you divide two numbers, you're going to get, well, let's be careful here. Will you always get another number? Let's think about this. 0 is a complex number because all numbers are complex. So this is actually going to be false. Because if I take, here's my counterexample, if I take any complex number, let's use 3i for an example, and I divide it by 0, I do not get another complex number. Even though this was a complex number and this was a complex number, this is undefined. You don't get another complex number when you divide it. Okay, the next one, number 26, all complex numbers are pure imaginary. Now, pure imaginary is like has just all imaginary parts, and that's going to be false because some are mixtures of imaginaries and real, like 3 plus 2i. If 2i is pure imaginary, well, 3 plus 2i is a mixture, so therefore it is not pure. Again, the word pure means without blemish or without flaw. Well, this is not pure imaginary. It has that other part to it. Number 27, a number cannot be both irrational and complex. Well, all numbers are complex, and that would be false because the number pi is irrational, but it's also a complex number because every number is complex. And then number 28, the product of a real number and a complex number is always a real number. And that's going to be false. And let's give our counterexample. Let's go ahead and write false. The product of a real and a complex, that'd be like 2 is real, 3 plus 2i is complex. Will that always be a real number? No. If you distribute this, 6 plus 4i, that is not a real number. That gives you a complex number back.